Welcome back, Physics 30. Today we are going to go through Unit B, Review Part 2. So when it comes to Part 2, I generally talk about several sections. One of the overlapping part between the review of Part 1 compared to Part 2 is basically energy, potential energy and kinetic energy perspective of electron and proton, any type of subatomic particle. And when it comes to next of that, we're moving from electric field on force and energy. I'm rather gonna go through magnetic force and field, something like that. All right, first thing first, let's talk about, and this is a little overlapping part. However, without it, there's no point of talking about magnetic field. Electric field and magnetic force. Now, first thing first, let's talk about field perspective. Field and force, actually they're kind of related to each other, but it's not exactly same. And there are multiple perspectives of it. When it comes to easy comparison of those, positive charge, when it comes to field, it's always going away from the source. That is electric field. When it comes to electron, it's always going toward. Now, what does that mean? That means electric field are kind of carved on stone for its vector. But when it comes to force, even the verb is different. We attract unlike charge together. So when we talk about the relationship between electric field and electric force, something that is not completely identical each other is theoretical perspective and characteristic perspective. These two. On the other hand, when it comes to something that is similar together, it's more of a formula because electric force is equal to Q times electric field. And that's when it's amount situation only. When it comes to these two, we generally use it when we talk about parallel plate. Like that. Why? Because electric field direction is always going like this, up to down. And electric field is uniform between different electrodes. Now, why this plays such a huge role? It's not necessarily about the force in that perspective. It's actually related to the potential energy. So here's my second part that I'm going to point it out. Potential energy versus kinetic energy. Now, long story short, ladies and gentlemen, potential energy, kinetic energy, they are not created from zero, or they're gonna just suddenly turning into nothing. It's conservation of energy theory. It just moved from one form to another form. So, in your system, whatever change of potential energy is occurring, that amount should be equal to your kinetic energy. And that part is undisputable fact in Physics 30, especially in this Unit B. Now my question is this. What's the relationship between those? There are several relationships if I think of anything. However, the one thing that I want to emphasize all the time is this Q delta V, that potential difference is what I want to emphasize. Now, when it comes to kinetic energy situation, we learned about this before. Basically 1 over 2m mv final minus vi, and it's more speed perspective. The only reason I'm putting velocity notion is so that I can differentiate between these two. And you may notice delta v is scalar, my voltage, potential differences, and these two should be your speed technically. But my v just look alike. However, let's see. When it comes to different scenario is what you need to be careful. What I mean by that is, let's see, how can I say? Let's think about it in this way. Some question use some term like this, initially at rest. Or some question, they say stops, something like that. So I look at these type of clue in detail because that means my initial velocity is 0 when it comes to this situation, but if I stop, that means my final velocity is 0. Why that play a huge role is because, well, you may notice that some of those will get canceled out. And by the way, I forgot 1 over 2 mv squared. So that's why I said it's case by case. When it comes to potential differences, I want to point that out. Depends on electron, proton, and alpha particles location. And what I mean by that is basically this. Let's say I have positive charge with a passable end over here, let's say, and negative electrode like that. If, for example, proton travel from one end to another end, you need to use full amount. But if it's from halfway, then you may notice it become half a potential. And that play a huge role because that ratio of potential difference actually equally apply for ratio of electropotential energy. That's why. So it is very straightforward. Now, one thing that I want to point it out to you is basically this. Imagine you're having speeding up situation. Then here's what you can think of. My kinetic energy final is gain from kinetic energy initial plus delta EP. You can getting into that notion. And I can just put like 1 over 2 mvi squared plus q delta v, something like that. This is a situation where you may start as a rest. You may have a speed originally. Who cares? It is speeding up. So when it comes to scalar perspective, it should be adding. Now, some situation, speed decline situation, or I like to say, I should have put this more, speed up versus slow down situation. That's way better. Make my life way easier. Speed down situation, you can think it in this way. Like imagine electron is coming from positive n all the way to negative n. You may notice that force, these two are attracting, those two repelling. So even if I have initial speed over here, my final speed should be definitely smaller because they will oppose the force to the other direction. I know it's acceleration talking, but let's talk about it in energy perspective. In that situation, what you need to do is my final kinetic energy is equivalent of my initial kinetic energy minus potential energy, something like that. In that way, you know that kinetic energy is actually smaller than kinetic energy of initial situation. We can do that. Sometimes people have a little tough time dealing with because they put Q as a positive versus negative, but I do not want you to think it in that way. Even Q value, think everything as an absolute value because that will help you more. Your rule of first step, which is drawing step and vector diagram, rather should inform you about whether it's speeding up, slow down. That's something that I want to point it out. We also did Millikan, but that's involved more heavily on the part 1. At least these situations involve more for the magnetic field. So why don't we go to our second half of Unit B, which is everything involved with magnetic field, magnetic force, and so on. Some technology, etc., etc. One thing that I want you to understand is when it comes to interaction between magnetic field and force and charged particle. So the very first thing that we learned is hand rule. And these hand rule, ladies and gentlemen, definitely involve a lot for magnetic field. And there are 3 different situations. The one involve current carrying wire and electrons. And when it comes to the second one, I want to point it out as coil wire and electrons. The third one is basically the unique one. This is the one that involves magnetic force, magnetic field, except it's external magnetic field, and electron or proton, depends. So we have those 3 rules. You guys need to remember when to use. Left hand for anything that's negative. Right hand, you have to use it for anything that is positive. So have that in your mind. So the very first rule. If I give you an example, this is a good example. I have electron that passes from diagonal right above to lower left side. Then it's a thumbs up, thumbs down situation. Except in this case, my thumb should indicate, I'm gonna kind of correlate my pen over here. My thumb direction should be my electron direction. So like that. And my forefinger that is curling around should be my magnetic field. So my magnetic field that is generated, which I call it induced magnetic field, should be like that. And that is my rule number 1. It is starting of the 3-dimension situation and depends on where you put the compass. If the compass is right above, then you know north will basically point this end because my forefinger will curve towards that. If it's below, then it should go to the other way. It's curling coming back, so north will point that direction if it's underneath this wire. So have that in your mind. When it comes to hand rule number 2, coiled wire, which is more known as solenoid, is something that you need to understand too. And let's say the electron is going to this direction and my curve is going front as a coming down and then front as coming down, something like that. Unlike the previous situation where your thumb represents the electron movement or proton movement if it's positive, when it comes to solenoid, it's other way around. My forefinger represent my coil direction. So as you may notice, it's going up, down, up, down, up, down, and going down is in front. So as my four fingers and my thumb is indicating the left side over here. So that indicate my magnetic field, and you may need to remember the magnetic field always connected because it's bipolar, north side on the left, south side on the right. Those are something that you need to also remember. Rule number 3 basically represent our ultimate situation. There's two application of it. FM is equal to ILB situation versus FM, that is QVB. Everything perpendicular to each other. There are two different situations. I'm going to use one of them as a left-hand rule, one of them as a right-hand rule. So let's go through the first example. This is a situation where current carrying wire is required. I'm going to go through like material way first. External magnets and actually, that's about it. Sorry. I thought I missed something. This is a situation where, for example, levitate, stationary, something like that may occur. And I'm going to explain to you what that means. Let's do side-by-side view. Let's say I have north of the external magnets and south of a external magnet, something like that. Now, one thing that you need to understand is magnetic field always go from north to south. Now, imagine my current carrying wire, and imagine it's going into the page for electron. Then my thumb need to go directly into the page, and my forefinger represent north to south, and my palm direction is the one that represent the force. So here's what you need to understand. My magnetic force goes up, but my gravitational force going down. So if it's stationary or levitate and being stationary, that means my magnetic force should be balanced up with my gravitational force. So you can have those relationships. Second situation is more unique. We need to think more three-dimensional for this time. Let's say my magnetic field by external magnets, basically, it's going out of the page. And let's say proton going into this field right now. Then you need to understand that my right hand is what I need to use. So thumb's going there, my forefinger is out of the page, so which is really hard to find out, but my palm is going down in that situation. And what's gonna happen is it's gonna make a circular motion. And in terms of force perspective, that is really interesting because that means my magnetic force is everything that I have in this system does is equal to my net force. But since it's circle, I get to this conclusion that it equals to Fc. So QVB is equal to mv squared over r. And velocity or speed, technically in this situation, because we're talking quantity only, those guys cancel each other. And if I isolate for, r, then radius is equal to mv over qnb, something like that. Any of the variable can be isolated in that perspective. And that is what we also cover from hand rule to calculation. Now, one of the last part, we need to understand that how can we, both theory way and calculation way, explain about actually, just theory way. I was thinking some unit C in there. We are not doing any other weird calculation based on that, but some induced magnetic field. So I believe that's 3. Or let me quickly check. Hand rule was number 1. Yeah. Oh, I forgot to put. Hand rule number 3 and calculation of force is number 2, sorry. And number 3 is my induced magnetic field and any type of magnetic field technology. I'm gonna list some of those that we covered. I want you to look through those notes. The very first thing about magnetic field technology we learned was a speaker and fire alarm type and motor. There are many different types other than these two, but have that in your mind. Speaker and magnetic lift, something like that. Induced magnetic field, if it's technology related, this is your electric generator. But the one that make this theory happen is Lenz's law. Lenz's law, think about it this way, it opposes motion. Although there are other examples that is available, I'm gonna directly go through some common example using solenoid. There is no direct attachment for the battery in each of the wire, but here's the thing. Imagine I'm bringing a magnet that going into the solenoid. So the motion is going left to right. However, because it's opposed motion, you're actually having some kind of versusing relationship. And that is my induced magnetic field effect. So how can I oppose it as a force perspective? There's only one way. It must be south on the left side and north on the right side, because that's the only way that vectors will fight against each other. If it's north, then magnetic field direction will be same and then attraction occurs, so it's completely opposing our Lenz's law. In order to make that relationship south and north, we need to use left hand rule number 2. That's the only way. Curve going up to the front and curve going down out into this page. So going like this. So electron will travel like that. This way we have not only induced magnetic field and induced electron because of that movement. And this is how we can generate any type of electricity by simply moving in or out when it comes to the magnets. But the one thing that you need to understand is it's only the flux is influenced by a motion as you enter and as you exit. If you already inside of, it can be any type of ring shape, let's say a wire that is inside, immersed completely inside of a magnetic field, then it doesn't happen. If it's already inside of the magnetic field, there is no induction occur. Only enter part and exit part, the motion either coming in or out, is the only case where we're gonna see induced magnetic field. This part is theory. And that is an overall review of magnetic field and electric field.